All right, let's unpack this. Think about the last time you're in a big apartment building, maybe a condo complex.
Yeah.
You flip a switch, plug in your, I don't know, your EV charger maybe,
Yeah.
and everything just works.
Right. It
Right.
seems simple on the surface, yeah. But the engineering, the sheer planning behind that reliability, that safety, it's all laid out. It's codified in this, well, this foundational document for construction,
Hmm.
the National Electrical Code, the NEC. That's it exactly. And today we're really diving deep into the, let's say, the guts of the NEC, specifically the 2023 edition, which is NFPA 70.
Okay.
And our focus, it's Chapter 2, Wiring and Protection. And within that, there's this absolutely critical set of rules for figuring out the total electrical needs. The demand for big places like multifamily dwellings.
Multifamily dwellings, so apartments, condos, that kind of thing.
Precisely. It's basically the systematic blueprint designers have to use to size the building's entire electrical service.
And, if you're learning this stuff, or maybe you're prepping for a meeting about design budgets, understanding how these specific calculations work, it's just crucial.
Absolutely.
This isn't just about, avoiding trip breakers.
Yeah.
It's safety, it's making sure the system lasts, and honestly, it's about avoiding massive cost overruns on the main gear.
Cost implications, yeah.
So our mission here is to uncover those exact factors, the mandatory minimums that really shape a modern building's electrical backbone.
And what's really interesting, I think, is how the code doesn't really trust guesswork or estimates. It forces designers to calculate this baseline load. Think of it like a non-negotiable safety floor.
So it doesn't matter if the tenant installs super efficient LEDs.
Doesn't matter. Or if they have some, ancient power-hungry stove. The code demands capacity for, let's call it the reasonable worst-case scenario.
Okay. So before we get into the nitty-gritty of the calculation, let's just get our bearings. Where does this wiring and protection chapter fit in the whole NEC structure?
Our sources lay it out right. Yeah, the NEC is pretty logically put together. It kicks off with Chapter 1, general. That's mostly admin rules, definitions, stuff like that.
Right. But right after that, bang, Chapter 2, wiring and protection. That's our focus. And it's foundational because it sets the basic rules for things like overcurrent protection in your breaker sizes, conductor size and your wire sizes. And those two things, breaker size and wire gauge, they're kind of useless unless you know how much power you're actually dealing with.
Exactly. You got it. Chapter 2 is the prerequisite before you even think about physical installation. It sets the protection rules and tells you how to figure out the load that protection needs to handle.
So it's like the gatekeeper. Determines the required capacity before you specify a single wire. Perfect way to put it. And that brings us right to the mathematical heart of this deep dive, section 220.84. That's the one dealing specifically with multifamily dwelling calculated loads. All right, section 220.84. So what's the core idea behind this specific calculation? Why this preliminary step?
Well, the main purpose is to establish the full required electrical load. Think of it as the absolute maximum theoretical demand.
Okay.
Before the designer is allowed to apply what we call demand factors. See, the code isn't naive. It knows that in a, say, 100-unit building, not everyone is going to run their AC, their oven, and their washing machine all at the exact same peak moment.
Right, that makes sense. That's the efficiency part you mentioned.
Yeah, that comes later. They use these efficiency factors, often from tables like 220.84b, to safely and realistically reduce the final service size. Makes it more economical.
But first,
you have to calculate the total load, almost as if every single light could be on, every appliance could be running flat out. And our sources, they list 5 distinct mandatory categories under 220.84c that you have to add up for this initial big calculation.
Okay. And this is maybe the aha moment for someone learning this. These 5 things. They aren't just an engineer's best guess, are they?
Not at all.
The code actually dictates specific numbers, specific volt-ampere figures that must be included.
Mandatory. It forces conservatism into the design. It basically takes subjectivity out of the equation for these minimum safety levels.
Safety first, right? Always.
Yeah.
And hey, speaking of safety and numbers, let's quickly define a term we'll be using a lot. VA, volt amperes. Okay, VA.
It's essentially the standard way we measure electrical load in the code. For a lot of these calculations, it acts pretty much like watts, but VA is the official unit here.
Good to know. So every time we say VA, think power required. Okay, let's break down those 5 required inputs, the ones in 220.84c that build up this baseline load. Where do we start? Okay, input 1, General lighting and receptacles. This is the base layer, you could say. What are the exact numbers the code demands here?
Right, the code is super specific. It says designers must include 33 volt amperes per square meter,
Okay.
or, because we often work in feet here, 3 volt amperes per square foot. That's for the general lighting and the general use receptacles, the standard wall outlets.
So it's purely based on the size of the living space. Floor area dictates this base load. Exactly. 3 VA per square foot. But hang on. Let me push back on that a bit.
Okay, for it.
3 VA per square foot. I mean, almost everyone uses super efficient LED lighting now, right?
Yeah.
Which draws, like, way less power than the old incandescent bulbs or even fluorescents. Isn't 3 VA per square foot?
Yeah.
Well, isn't it kind of wildly conservative? Does that force builders to oversize things?
That is a fantastic question, and it really gets to the heart of the NEC's philosophy. Its primary job isn't energy efficiency. That's important, but it's secondary.
Okay, so what's primary?
Fire safety and reliability. The code has to account for the worst case, or at least a very demanding case. What if a tenant puts in older high-draw lights, or plugs in space heaters, or, runs multiple high-draw things from those general outlets?
Ah, I see. So that 3 VA per square foot isn't about the typical load with LEDs.
Right. It's about ensuring the wiring, the protection,
Yeah.
the infrastructure can handle a potential maximum load dictated purely by the dwelling size, period. It builds in that safety margin regardless of the tech being used right now.
Okay, that makes sense. Get the universal safety net kind of baked into the square footage.
Couldn't have said it better.
All right. So we've got the baseline for lighting and general outlets calculated based on area. What's input number 2? Input 2 covers those dedicated higher draw circuits you find in pretty much every unit. Small appliances and laundry circuits. Yeah. Kitchen counters, laundry room.
Exactly. For this second piece, the code says you must add 1500 volt amperes for each required small appliance branch circuit in the kitchen. And you also have to add another 1500 volt amperes for each dedicated laundry branch circuit.
Okay, let's translate that code speak. The references in the source, 210.11C1 and C2, those are the standard required circuits for kitchen counters and the washing machine hookup, right?
Press them.
So if a typical apartment needs, say, 2 kitchen circuits and 1 laundry circuit, that's boom. An automatic 4500 VA added to the calculation, 1500 plus 1500 plus 1500.
Precisely. Just like that. It ensures those circuits, the ones that see heavy temporary use, think blenders, toasters, hair dryers, irons, have this fixed conservative capacity already factored in. No guesswork about what might get plugged in.
Okay, so area-based load first, then these fixed VA amounts for specific circuits. What's next? Input 3.
Input 3 is the fixed appliance group. Now, this is where the specific equipment choices for the building really start to matter, because this part relies on the nameplate rating.
Nameplate rating.
Yeah.
So what's actually stamped on the appliance by the manufacturer?
Well,
exactly that, the official rating. The code is very clear. The designer must include the nameplate VA or wattage rating for a specific list of items. Okay, what's on that list?
It includes all appliances that are fastened in place, things like garbage disposals, maybe hardwired dishwashers.
Ceiling fans, too?
Yeah.
Anything permanently connected or located on a specific circuit that's not covered elsewhere. But crucially, it also forces you to include the big kitchen players based on their nameplates, ranges, wall-mounted ovens, counter-mounted cooktops. Makes sense. Big loads.
Huge. Also, clothes dryers, unless they were already covered by that 1500 VA laundry circuit we just talked about in input 2. If it's a separate higher power dryer connection, its nameplate goes in here.
Okay. So you don't double dip on the dryer load.
Right. And finally, water heaters. Their nameplate rating must be included here too.
You know, it's interesting why the code insists on the nameplate rating, it feels like. Like it's shifting liability almost, ensuring the calculation uses the objective measurable number from the manufacturer.
That's a really sharp insight. I think you're spot on. The nameplate is the legally binding number from the maker. It locks the calculation to the actual equipment.
So a designer can't just, like, calculate for a small water heater and then let the contractor install a much bigger one later.
Exactly. If the calculation used a 4 kW water heater spec, but a 6 kW unit goes in, poof, there goes your safety margin. The nameplate requirement prevents that kind of mismatch, and it anchors the calculation to reality.
Okay, so lighting outlets by area. Fixed VA for appliance laundry circuits. Nameplates for major fixed appliances. What's input 4? Sounds like it might cover things outside the actual apartment unit.
You got it. Input 4 is about permanent motor.
Permanent motors.
Yeah, this one's pretty simple but important. You need to add up the nameplate ampere or kVA rating of all permanently connected motors that weren't already captured in that fixed appliance group, input 3.
So think about like common area equipment.
Exactly. Pumps for maybe landscaping irrigation or a fountain, fan motors for ventilating hallways, or maybe the big motor for the shared parking garage door.
Right, stuff that serves the whole building, not just one unit. They might not seem like much individually, but they add up and they run often.
Absolutely. They contribute a steady or frequent demand to the building's main electrical service, so they definitely can't be ignored in this initial load calculation.
Okay, makes sense. So
Yeah.
that brings us to the last one, input 5. And this one deals with the really big energy hogs, right? Heating and cooling.
The biggest variable loads in almost any building, yeah. Heating versus cooling.
Now, this one seems a little different. You mentioned earlier it has a kind of built-in efficiency assumption, unlike the others. How does the code handle this?
This is actually one of the clearest places where the code makes a rational and conservative assumption about how a building operates to prevent massive oversizing.
Okay. The requirement is you only need to include the larger of the two loads, either the total air conditioning load or the total fixed electric space heating load, whichever one is bigger.
Ah.
So the logic is you're either running the heat full blast in the winter or the AC full blast in the summer.
But very, very rarely are you doing both at maximum capacity at the exact same time across the entire building.
Right. That makes practical sense.
It does. And by only taking the larger of those two major loads, the calculation stays safe for the peak demand season, whichever it is, but it avoids forcing the designers to size the main service conductors, the transformers, all that expensive gear.
For a combined load that will almost never actually happen.
Precisely. The cost savings just from that one logical assumption, not doubling up on heating and cooling loads, can be absolutely substantial on a large project. It prevents major, unnecessary expense on the main electrical gear.
Wow. Okay, so let's try to connect this back to the bigger picture then. It's a really clear illustration of how the code drives not just safety, but design and cost too. You've got these 5 mandatory steps.
Yep, 5 distinct inputs.
Starting with that conservative 3 VA per square foot for the general ambient power.
Right, the baseline.
Then adding fixed 1,500 VA chunks for those dedicated kitchen and laundry service.
Mandatory additions.
Then meticulously documenting the nameplate ratings of all the specific big fixed appliances.
Using the manufacturer's number.
Accounting for every single permanent motor, even the ones outside the units.
Can't forget those.
And finally, making that smart choice between the heating load and the cooling load, taking only the bigger one.
That's the whole process in a nutshell. The code just systematically forces you to factor in everything using specific required figures or relying on those official nameplates to establish that total initial calculated load for the multifamily dwelling. That number becomes the bedrock, the anchor for everything else.
And for you, the listener, really digging into this level of detail, it just highlights the incredible precision needed in modern electrical design, doesn't it?
Yeah.
Chapter 2, wiring and protection. It's not just about picking wire sizes. It's about laying down this mathematical, non-negotiable foundation for safety, for reliability, for long-term performance.
Yeah, and, thinking about this as we wrap up, it does raise an interesting question, especially when you look ahead.
Oh.
Well, we've just walked through how many mandatory kind of fixed calculations are needed just to start sizing a system based on today's typical building tech, right?
Yeah, it's quite a list.
So consider what's coming or what's already arriving. Things like shared banks of high-speed EV chargers in the parking garage. That's a huge variable load. Or mandatory integration of building microgrids, or maybe distributed solar power on the roof feeding back in.
Yeah. New demands, new technologies.
How are those going to get folded in? They'll inevitably require new, equally specific, equally mandatory rules and calculation methods to be added into this existing NEC structure, wouldn't you think? The rulebook has to keep evolving just to keep pace with how we use power tomorrow.
That's a great final thought. The rulebook is never really finished, is it? And those margins for safety and capacity, they just keep getting tested by new technology. A really fascinating deep dive into the mandatory minimums of the NEC.